So, Harsh, are you ready? Can we start?
Yep, yep, yep.
Okay, before that, I would just like to do the formal proceedings. You going to share something on the
Should I share my screen?
Okay, we'll do it a bit later. So let me just first begin. So a very good afternoon to all present here. I feel very happy to have Mr. Harsh Mishra here. So I would like to share a brief introduction about him. And sir, before we actually go into the introduction, I would like to welcome you for the technical seminar that has been organized by CSE department, IoT, and ENCS departments together. So we have the students from cybersecurity, IoT, and ENCS branches here. So on behalf of all of us, we would like to extend a hearty welcome to you, sir. A very warm welcome from all of us. And thank you for consenting and agreeing to do this session for all of us and getting deeper into the domain of machine learning and deep learning. So before we actually begin, I would like to briefly give a introduction about Sir. So Harsh Mishra Sir is a meritorious alumni of TCET. So he has done his B in computer engineering from TCET, and he has worked as a front-end developer in AY International Private Limited. He's also a well-versed deep learning trainer at Imarticus Private Limited. Also, I feel happy to share that he's pursuing his PG, that is MTech in AINDS. He has published around 3 research papers in the last 3 years in the domain of AI. And one of the key achievement that obviously no one would forget is he was the winner of SIH 2022. Fortunately, we were all in the same team. So, and it was a great experience working with him. So, I asked him to conduct this session for our students, and he immediately agreed. So, thank you so much, Harsh, for that. And so, without delaying further, I would like to hand over the session to you, and you can start with the session.
Thank you, ma'am. It feels really different to be an alumni. And we were
The
together
students
for the
connect
time, right?
better. So that's
Yeah, yeah, yeah. And I remember you got your PhD on the day we won SIS, so it was a very memorable day. So I'll share my screen and I will share my screen. Is my screen visible?
yeah, we can see the
Is
I
it?
think I guess you shared the entire screen. So
I think now I'll just.
yeah, yeah, yes.
Okay. Okay. So uh, this is the topic that we are going to discuss today. I hope it becomes an interactive session. Please try to unmute and say. Don't type on chat. You can type on chat if there is a if you are not able to unmute. But I would say that you should unmute and speak because it becomes easier for me to have a conversation. And today's topic is machine learning and deep learning for plant disease classification and
रिक्वेस्ट थी ABL का जो
okay and AI advancements. The reason why I chose this topic was there are a lot of keywords in here, right? If you look at the title, it has machine learning, it has deep learning. There's the word classification, which is also very important word in the domain of AI and AI advancements. So at the end of the session, I would be trying to uh, give you a brief note about what's happening right now and where we are headed to. Okay, so I hope that you get interested in this. All right, let's start with one of these keywords that is AI. Right, I'll try to keep this in Hindi and English. If anybody has any issues, if you cannot understand, you cannot hear, you are obviously free to interrupt and ask me to repeat again. Okay. So let's start with the term AI itself, artificial intelligence, right? So can we answer this question? What is intelligence? Anyone? What do you think? What is intelligence? Anyone can try this. Uh, how many people are there in the meet? Around 59. Okay, so it's a good strength. So can we so, what is intelligence? Can anybody attempt this question? What is intelligence? Because you see, we are living in the era that now machines have started talking to us, isn't it? Now we have ChatGPT, and ChatGPT is not a simple chatbot. It can do a lot of things. You can talk to it. You can talk to the chatbot, and you can give situation. You can ask him to take a decision, so it is more than a chatbot now. It's very important to understand this word intelligence before we actually try to understand artificial intelligence or machine learning or deep learning, right? So in very simple words, if I tell you, intelligence is made up of few keywords. Again, I would say pattern recognition, creativity, imagination, and emotional intelligence. So these are the four important things with which, when combined together, is known as intelligence, right? And this I'm talking about the human level intelligence. So this is human level intelligence, or you may say the common sense that we talk about. We talk about common sense. Humans have common sense, which probably other species do not have that kind of development in their common sense. So we are different because we have this common sense, which has ability to recognize pattern. We are creative. We can imagine new things, and we are emotionally connected to other things because we have emotional intelligence as well, right? So this entire thing is intelligence. If I ask you, uh, do you think that today, as we are sitting here and discussing this, are machines having such kind of intelligence? Do you think machines are able to recognize pattern? They are creative. They can imagine and they have emotional intelligence. Anyone? All right. Probably the answer is no. Right? So machines, what is happening is machines are not yet developed so much to get this kind of intelligence. So what is the term artificial intelligence when we talk about if they are not able to achieve the intelligence? So the artificial intelligence that we are talking about today is only somewhat good at pattern recognition. Today's AI systems are not that creative like humans. They cannot imagine. Although there is a field of deep learning where researchers are figuring out how is there a way that an AI system can dream or can imagine, that is deep dream. That's a different domain, but there is no significant or breakthrough we have gotten yet. So I would say that we are not still able to develop a machine that can imagine well, and emotional intelligence is probably the last thing you would get. So this general intelligence, the day when we achieve this, that is not AI, that is AGI, which is artificial general intelligence, because the intelligence that we say today, yeah, am I audible? I don't know how I got it. I got it. Okay, yeah, I'm audible. Right. So AI today is a subset of human intelligence focused majorly towards pattern recognition. So the artificial intelligence that we are talking about today is only able to somewhat recognize pattern. Now this, I would actually tell you, they are better than humans in this AI systems. Because the reason being is the kind of algorithms that we develop is particularly meant to recognize the pattern. Okay. So the algorithm that we have developed is particularly made to recognize the pattern. That's why AI is really, really good in able to recognize pattern. Okay. So the intelligence that we were talking about is AGI. That's not AI. That is artificial general intelligence. And many people debate that it is very near, or personally, I think it would take a long time. But the advancement in this field is very, very rapid. So you cannot say anything for sure. Now let's see the history of AI. Now, you would be thinking that artificial intelligence is a newer term, okay, and now we are talking about it, and now we are getting the products of it. But honestly, it's a very, very old concept. And in fact, from the moment we had machines, we started with calculator, then we developed computers. When when we started developing machines, humans always had this crazy idea to think that if machines get smarter and they start talking to us, or maybe they start thinking like us. So it started in 19 from the 1950s itself. So if you look at the symbolic AI, that was a dominant paradigm of AI research from mid 1950s. What happens is there was a huge wave of symbolic AI in 1950s, and we used to think that time, teachers used to think that this is AI, but we realized it later that this is not AI what we are talking about. What they did was they created a huge knowledge system that was built on an if-else condition. So if this is the case, do this. If this is the case, do this. If this is the case, do this. Right. So this is not actually intelligence, because intelligence is not simply decision making, but what goes behind the decision making. If you are explicitly programming that for this condition take this decision, for this condition that take this decision, that is not intelligence. What happens if some sudden queries arises? What happens if an unexpected situation comes up? Are you able to decide it then? Actually shows your intelligence, isn't it? That happens in real life as well. So in 1950s till 1990s, what was happening was symbolic AI was doing pretty good. People were building huge knowledge systems that was on if else condition, and then we moved to expert systems. So in mid 1990s, we switched to expert systems. Probably you would have this AI subject in your engineering, and you would be learning about expert systems there. But I'll tell you, expert systems took symbolic AI one step further. So symbolic AI had this huge knowledge system, or you may say a knowledge database. And then what happened? So now expert systems put another layer, that is inference engine. So now the inference engine was taking a decision based on the knowledge that was stored in the database. But the problem is, see, the problem is if I tell you that you need to identify a dog. If I give you picture of a dog and I'll ask you whether there is a dog present in this picture or not, it's a yes no question, right? Yeah. So if I ask you whether a dog is present in the picture or not, it's a yes no question. Yes, the dog is present in the picture, or no, it is not. But the problem is that there are many breeds of dog, and each breed have different characteristics. So, how many if else condition you are going to write? That is the question, right? Uh, the best example of expert systems were the chess game. So we started playing chess with computers really early on, and that really felt like an AI's agent, because the computer was playing the chess, and it was not just playing the chess; it was also able to defeat human till certain level. So that was the expert system, because it had the knowledge base and it had the inference engine. Now I don't want to talk more on this, as we'll cover this on your syllabus. Also, it is completely irrelevant today. We do not work on systems like these anymore. So it looked promising initially, but it failed in the fuzzy logic problems, right? So what is a fuzzy logic problem? Fuzzy logic is basically where you need some sort of intelligence where the logic is not so simple if else, right? You need to make certain adjustment in your logic. You need to think of other circumstances too. So that fuzzy logic problems, obviously, it was not able to take decisions. Okay, I hope I am clear till here. Right. So for fuzzy logic problems, what could we do? That was the question. Because knowledge systems, expert systems were not able to perform well. And then what happened? A new terminology, you would say, or a new field of study of statistics came out, and that was machine learning. Now before I start this, if I check, we have 71 people in the meet. Uh, can anybody share anything? Have you heard the term machine learning? If yes, can you define it in your own language, in a line or in a couple of lines? Anyone? Because I'm pretty sure you would be hearing this term for a long time. Yes, anyone? Uh,
Students, you can unmute yourself and tell.
okay. So I'm assuming like none of you have heard this term machine learning because it's not possible. All right, no problem. I'll take that as a no. Probably you wouldn't be familiar, or I don't know why you are thinking before responding. You don't have to think that much. Simply, you can share what you have heard. Right. So, machine learning. This term actually consists of two things, right? We have machine, and then we have learning, right? We have machine, and we have learning. Uh, Now, if we talk about what is machine learning, one line definition is it's all about learning from data, right? This is all machine learning is about. In fact, entire AI, it's all about data. Today, data is the most valuable asset. The most valuable asset is data. What we are doing in machine learning is we are making machines smarter, right? Obviously, in comparison to what machines used to be before, today machines are much more smarter. But how are we increasing the smartness of the machine? Is by allowing it to learn from data, from a real world data, the world that we live in, real data, right? Now, how we do that, that's a really important question because if you see machine simply understand ones and zeros, right? A machine have binary language understanding. It cannot understand English. And even today, when you're talking to ChatGPT, it does not understand English the way you understand it, but it converts it into binary numbers and then it does a lot of computation behind the scene. So the only way to make the data relevant to the machine is by using mathematics and statistics. And that's how actually our brain works too. But we do not think it like that way, right? We say that this person is very experienced. What does that mean to be very experienced? It means that he has been in a similar situation before. He took a decision, that decision gave an outcome, and he learned from that outcome. And every outcome is mathematical in nature, right? If I'm making a deal, I may be in profit, I may be in loss. Sometimes if I take some actions, I may be in profit in money, but mentally if I'm disturbed, I would quantify that as negative amount. And I would say that this work although gives me good money, but it is not able to give me good sleep. So maybe I'll quit. So every decision that we take, every experience that we have is some sort of mathematics in itself. So now we use these mathematics tools, the statistics tools, so that we can make sure that machine understands this data and gains an experience. That is learning, right? How do you learn? From an experience, from an incident, from a decision of yours. Now, what is learning? It's very important to define learning. Right now, the machine learning that we are working on is to find the pattern. So machine learning uses statistics to find a pattern and learn from it, right? That's what we do in real life as well. If you're talking to some person, if I'm an old friend of yours, I would know what things you like and what things you don't like because you have a pattern of reaction. If I do these things, you react another way. If I do these things, you would react another way. So I know what you like and what you don't. So I would behave in front of you accordingly, or the machine will. So it's important to learn the pattern. Pattern is data gives pattern, right? What data is useful for to give you the pattern? Because we know history repeats itself, and that's true. We see in data and we try to predict that because we have an understanding that history will be repeating itself. So what we can learn from history is pattern. Now, these patterns helps to predict on an unseen data. Now, this is the entire aim of machine learning or artificial intelligence or deep learning is these patterns help us to predict on the unseen data. So, why we are learning? To predict on the unseen data, to make better decisions in future, to get ourselves prepared. Okay. Now, this is a typical, I hope you can see the output. This is a computer, typical computer. In a computer or a system or any electronic system, you give two inputs. You give the data and you give the program, and then you expect an output. For example, a simple calculator. So if you have a simple calculator in your hand, the program is already fitted in the calculator and then you provide the data. You say 2 plus 2 is what? So the program tells how to add the two numbers and then data, what it does, data is given by you. So it fits in the program and the output is given 4. That's perfect. 2 plus 2 is 4. Perfect. Now, this is how a normal computer would work. One data input, one program input, and one output would be the output of the system. Machine learning algorithms work in a different way. You give the data and the output to machine learning algorithm, and it will give you a program as an output. This program here that I'm talking about is you can understand this as a pattern, right? So the pattern that we have recognized, right? So the pattern that we have recognized. Right. So I hope this picture is clear to you, and there's no issue here. Now, when is machine learning useful? This is also an important question. When is machine learning useful? So, machine learning is useful in many cases, many conditions. Here are the three things that I've explicitly mentioned. First, where the condition changes over time. Example, email spam classifier. So now you have a spam section in your email. If you are using Gmail, there's a section of spam. What happens if I do not use an machine learning algorithm and if I explicitly code an algorithm that detects whether the given email is a spam or not, I would write a condition that if the word discount is used three times in an email, put it in the spam box. But what if somehow the person who is sending the email learns this information? That if I put discount thrice or more than thrice, my mail is going in the spam box. So what will he do? He will reduce the number of discount and now he will only put two discounts. And what if you say instead of discount, he will change the word to reward or to award. So these conditions might change over time, and it is not humanly possible to keeping up with those changes, right? So in such cases, machine learning can be useful where you do not explicitly code, you do not explicitly say whether this is spam or not, but again, it's a kind of fuzzy logic, When humans think about a lot of things and make a decision, machine would be able to do the same. Second is where conditions are too much. For example, image classification. I already gave you an example of dog classification, dog image classification. So if you see, there are so many conditions to identify a dog, and then there are so many breeds of a dog. So are you able to write all the conditions for every breed? I don't think so. It's possible. Even if it's possible for dog, there might be another problem statement where it's not possible to write so many conditions. And that's why expert systems failed, and that's why we are using machine learning today. There is another very useful, important term that is data mining. I'm pretty sure if you are a computer engineer, you would be having this subject probably as an elective subject. What we do is we pick correlation and patterns of data using machine learning. So what happens is, for example, email spam classifier. So a mail comes, and my machine learning model says that this has to go in the spam box. So now I can ask my machine learning model, why did you put this in the spam? So what was wrong in this mail? So that is data mining. So that this is actually reverse. We are picking up the pattern using machine learning, right? There's another term called as explainable AI, which is very in demand today. We'll not discuss that, but this is when machine learning is useful. Right now, if you have listened to me, I just said that data is the most important and useful asset a person or a company or an organization can have today. Data can be internal organization data or can be a real world data that is publicly available. Data is the most important thing because today we are living in the era of data. The amount of data that is generated is is, is exceptional. It's very huge, right? So we are able to create a huge amount of data today. And what we are doing that we are taking the data, giving it to machine learning model or AI algorithm, and then we are training that, right? So data is very important. I'll tell you a small case study. Uh, if you know Walmart, right? Walmart is in US. They did this case study, or probably another big chain of supermarkets did this. But I guess it is from Walmart. What they did is before they open a store at a particular location, they look at the data of the location. How many people live there? What is their annual income? What is the gender ratio? How many female lives there? How many males live there? What is the average age? And all sort of that data. So what happened is, I'll tell you what they did is they realized that in this area there are a lot of young parents. Okay, there are a lot of young parents, and what they did was weekend was coming, so they realized now weekend is there, so people will chill, right? So they'll buy? They'll buy beers, right? And because they are young parents, they have very young children. So probably what you'll do, they'll buy diapers, right? Because you fill up the stock at the weekend, you don't buy diaper every day. So they put two racks together, one of diapers and one of beers together, and they saw increment in their sales. So this is how you use data, you analyze data and take a decision for your business. Okay. There's another very interesting fact about data is if you look from the start of our planet till 2015. Okay, so from 2015 you go behind and you keep going. In this amount of time, the digital data that was generated alone in 2016, twice that amount was generated. And special thanks to Geo. Geo was launched in 2016, and now suddenly the entire India is online. Before that, very few Indians were online. So now we have this huge stream of data that is coming our way. I have mentioned some facts. Like 90% of the world's data has been generated in the last 2 years, which is true. Very tremendous amount of data has been generated. Data centers now consume more power than some countries. There's a theory. I'm not sure if it's true or not. I've read this somewhere. For every prompt you ask ChatGPT, I think it for every chat it requires 30 or half a liter of water because you need to keep the system cool. To keep the system cool, you need to put air conditioners, and air conditioner requires water to work, isn't it? And by 2025, 463 billion gigabytes of data will be created every day. So 463 billion GB of data is created every day. Every minute, 500 hours of video are uploaded on YouTube. It's an old fact. A lot of people are uploading videos on YouTube. Facebook generates 4 petabytes of data per day. 5.3 billion searches happen every day. Every day, 306 billion emails are sent, and on platforms like Instagram, over 95 million photos and videos are shared each day. So you can see the data is actually very huge. Right. So the data that we are working today for plant disease classification is the plant release data. So if you look at the data, if you look here, we have 20639 images, so around 20,639 images we have, out of which Pepper Bell has around 1478 images, healthy, and 997 diseased. Potato has 2000 diseased image and 152 healthy, and tomato has around 1591 healthy images and 1442 one, that is 14,421 images of 9 different diseases. So if you look, there are multiple disease data that we have for the plant village data set, right? And what was the problem statement? We will use machine learning and deep learning to detect plant or crop disease. Okay, so here is a few example. So if you look, this is potato late blight. This tomato late blight. So late blight is actually a disease. If you look, the shape of potato leaves and tomato leaves are very different, right? Okay, wait, let me just. We are waiting on people. Can somebody mute him? I don't know. Okay, thank you. Okay, right. So coming back to where were we? Right, we were here. So I hope you can see this tomato late blight and potato late blight. So these is certain example. If I show you my data set, uh, yeah, let me go here. Right. Is it visible? Is this file visible? This directory? Anyone can confirm? Can you see this?
Yes, sir.
Okay, thank you. So I can randomly open any directory. Let's open Pepper Bell bacteria spot. Right. So these are the images, right? These are the images of Pepper Bell bacteria spot. So this is the data. So basically, I'm trying to tell you what data we have in our hand right now. Okay. Now the total data that we had was how much? 20,000 images. But there is one small problem here, and the problem is if you look, mosaic virus has only 373 images, which is very less because yellow leaf curve has 3,000 images, and every other disease has more than 1,000 images. So my model would never actually learn what a mosaic virus is because it would see, okay, we have only 373 images. It would be either ignored or it would be overshadowed by some other disease. If you see potato health, there are only 152, and whereas everybody else has at least 1,000 images. So this is an example of imbalanced data. That there are few classes which are very less in number, and that might be ignored by the model, right? So what is the solution to that? We'll come to that. But now you look at this business problem understanding. This is the data science life cycle. So every project that you make, either it's an AI, ML, DL, data science project, you follow this pipeline. Okay. And how do you start? You start with uh, we need to start with understanding business problem. Uh, very important. You cannot create a model without actually understanding what business this model would be used for. Because why do you need to understand that problem? Is because it will help you to collect the relevant data. If you are collecting irrelevant data, for example, I want to calculate or I want to predict a house price. Now, for predicting the price of house, I need to first understand what are the factors that are actually responsible for a good house price. Is the locality is good? Is there a nearby hospital or a school? How many bedrooms are there? What is the size of bedroom? How many? What is the size of kitchen? So these are the factors that really affect the price of a house, right? So if I'm working on house price prediction, I should understand the problem, that what data I need to collect. Once you understand the problem very well, now you know that I need this kind of data and I need this kind of algorithm to work on it. So you have collected the data. Now what happens? You would say data cleaning and preparation. Whatever data you collect from the real world, what happens is it might not be in the best format. There would be some missing values, there would be some duplicate values. What happens if I ask you to fill a form, there would be a chance that somebody left or forgot to fill a cell, or maybe somebody has filled the same form twice. So there are a little bit need to go into the data, look into the data and clean the data and prepare it for the model. Once you have a good data, you start analyzing the data. That is EDA, that is exploratory data analysis. Okay, so you analyze the data, what the data is saying to you. If I have the complete data of cricketers, right? If I have data of IPL, what analysis can I do? Who is the best batsman? How do you know who is the best batsman in IPL? Probably the batsman with the highest strike rate, with the most number of sixes, with the most consistent average, or whatever you may say. Who is the best bowler with most number of wickets, with the least economy and the best average. So these are the factors that you go and you ask data, you ask a question, and the data replies you an answer. Then comes feature engineering. This is very important. Your machine learning performance is directly proportional to how well feature engineering you have performed. What is feature engineering? Very simple. The inputs that you give to the machine learning model is your features. What does a machine learning model does? It takes inputs and gives an output. For example, house price prediction. I want to predict the price of an house. So what would be the input? Location. How far is the airport? How far is hospital? How far is the school? How is the roads around the house? How many bedrooms are there? What is the size of the bedroom? How many washrooms are there? Is the washroom attached to bedroom or separate? So these are the inputs that you give to a machine learning model, and they will give you an output. That considering everything, I think that this is the correct price of the house. So these inputs that are going are actually called as features. So what feature engineering is to make sure that you collect the best features that influence the model. right? If for house price prediction, if you are considering house price prediction, uh, certain data might be invaluable to you, right? For example, what can you think of? Uh, do you have an NGO nearby you? If you ask this question, that do you have an NGO around the house? Nobody cares, right? Because that does not affect. But do you have an industrial area around you? That affects the price. So you need to perform certain steps to make sure the feature that you are selecting and the format of the feature has to be in such a way that your learning happens very nicely. In this problem statement, we will do some feature engineering and I will show you how it is actually done. For an example, if I have two column, there is a data, Titanic data. I'll see if I can show you the Titanic data. Uh, Let me quickly check this. I had stored Titanic data in my SQL server, but let's see if I have it right now or not. Okay, I have this. Can you see my SQL server? Yes, is it visible?
Yes.
Okay. Have you heard about this? I'm pretty sure you know this, right? Database, SQL, basic queries at least. Are you familiar with this?
No.
Anyone? No? Okay. It's a database, right? It's very important for if you are doing computer engineering. At least it's very important. Now, if this is the Titanic data, so this is the data of the people, those were present at the Titanic. Now, this is not the complete data, but it is a subset of the data, right? And if you look, if I select star from train, uh, uh, if you look, what columns do I have here? I have here passenger ID, survived yes or no. 0 means no, 1 means yes. So this passenger could not survive and this passenger survived. Class is the class in which the passenger was traveling, the gender, the age. Now this is sibling spouse and this is parent child. So SIB stands for what? How many sibling spouse this passenger had on the Titanic ship, and how many parent child this passenger had on the Titanic ship. What was the ticket, fare, and embarkments from which station he onboarded. So if you look here, this data, sibling, spouse, and parent child. For these data, I can combine and create a new column that is family members because sibling, spouse, parent, child are your family members. So instead of having two columns, I can combine and I can create a one column so that my computations are reduced. If you look name to predict whether a person will die or not, you don't require the name of it, right? So you will remove this. So first of all, you need to have a problem understanding, and then you need to perform some feature engineering. So this is what I wanted to show, right? Uh, right. And then machine learning model happens. Then you evaluate the model. Then you visualize. Data visualization is there. Basically, you visualize the model performance. So if you look, the data was imbalanced, right? I think unbalanced is the wrong word. Imbalanced. Data was looking imbalanced. So what I did was I did some augmentation to increase the number of images. So I took one image and created four copies out of it. So if you look, this is like this. If you see, this is one vertical. I tilted it like this, and then this became like this. If you see, the diseased part was here, and now here it is here. So I have flipped. Okay, so it's an horizontal flip, right? So similarly, I have done this kind of augmentation on the data which were less in number. Now it's very important to understand. that this image that you have for a computer, it is not a simple image, but rather for a computer system, it is an array of numbers. For a computer, an image is a two-dimensional array of numbers or a matrix. So if you send an image to computer or to any electronic system, it does not see the same way as we see because we have human eyes. We can see things. Computer cannot see things. It can read the data. So what an image is? An image is a matrix of numbers. Now these numbers may be from 0 to 255. So if I zoom in, if I zoom in, you see these are zeros. Can you see here zeros? Zero. Completely black means zero, and completely white means 255. Okay, and these numbers are known as pixel values, right? So whenever we buy a phone, we ask how many pixels are there in the camera lens. That means when you click a picture, how many pixels you are going to get. Okay, so this image that you are seeing, this image is for ordinary eye, but a computer looks it as a matrix of numbers. I hope this concept is clear to you, right? So if you see in between it here where there is nothing, the numbers are small 0, 1, 2, 3 because there's no color means 0, and brightest color that is white is 255. So the range is 0 to 255. So if you see here's 255 value is used. That means this is completely white. This is gray, so it is 212 and so on. Okay. So I hope you get an idea of this. Right. So now we will discuss some feature engineering techniques. Now these techniques that are discussed here are particularly used for image data. For non-image data, like for a number data, feature engineering is not that complex. But feature engineering in image data is can be a little bit complex image when you compare it with other techniques. But it's important because when you give the right features to the machine learning model, it may learn the right thing. Right? So the first is color histogram features. Okay, so if you have studied histogram a little bit, you would know that histogram is basically the count of frequency. Histogram is the count of frequency. It's a plot of frequency. Now you see there are three colors here: green, blue, and red. Okay. Now I told you that an image is a two-dimensional matrix for a computer, but it's a two-dimensional matrix only for a black and white image. Okay. For a color image, it's a three-dimensional matrix. So where is the another dimension? What happens is when you are giving a color image, a color photo, A, any color is made up of three colors: red, green, and blue. These are the primary colors, and every single color is made out of these three colors, right? So we have three layers, one behind another. This one layer you can see here. Imagine there are two more layers behind this, and when three layers are there, okay, in one layer there would be a pixel value. Let's say I'm talking about this corner. Assume it's a color image and there is some random color in it. Okay, so that color would be made up of red, green, and blue. So I would have three channels. These matrices are also known as channels. Okay, I would be having three channels: red, green, and blue. So let's say this is the first channel, red channel, and we have a red value here. Behind it, there is another green channel. There would be another pixel value assigned to it, and behind that, there is another channel, okay, which has some blue pixel value. When you club those together, when you stack it in one in front of another, you get a color image. Okay, let me try to show you RGB image channels. Let us look if I can show you. Right. See, this is what I'm talking about. Can I zoom it? Yes. You see, now this is a very colorful image, right? It has some blue, it has green. This pipe is there. This is red. This is white. Now these images are made up of these colors are made up of three colors, right? Red, green, and blue. So this is the red channel. This is the green channel, and this is the blue channel, right? When they are stacked together, when they are kept together, you get this image. So a colorful image is a three-dimensional matrices, is a three-dimensional array or a 3D matrix like this. If you look here, okay. Yeah. So this is what I was talking about. Okay. Now uh, let's come back. Right. So first way is what I'll do. I'll create a histogram. Histogram is basically I will count how many pixel values are present in what range. So if you look here, this what it is telling you. This is the range. It starts from zero because pixel value is from zero to 255, right? So this is 250 and this is 255. In this given image, the image that you are seeing on the screen here, on this image, I saw that the red pixels, we have three channels, right? Red, blue, and green. In a red channel, most of the pixels were of value 200 to 250 because you see this image has lot of red in color. I hope you can see a reddish type of scale, right? So what is happening here? You can see lot of around 4,000 pixels are from value 0 200 to 250. So what I'm doing is I'm calculating the frequency that this particular frequency, this particular intensity level or this particular pixel value, how many times it is occurring, what is the frequency. If you see, green is somewhat here. So majorly green is from between 50 to 150 and blue. So green and blue are very less in this image and red is more. This is what I'm trying to give this information to the machine learning model. Because machine learning model ultimately understands what? Numbers, right? It's a machine. It will understand numbers. If you give an entire image, it won't be able to learn anything. So I'm extracting numbers out of it. So what number should I extract? I am able to find the pattern that this image has more red pixels. This image has more this many pixels. So the machine is getting an idea that how a dog looks, how a woman looks, how a man looks. How okay in dog this pixel is more in a man this pixel is more in a woman this pixel is more, right? So this is a feature engineering technique. Another we have is a GLCM feature. So GLCM is gray level co-occurrence matrix. Now don't worry, it's very simple. Imagine this is your image. This is your image. Okay. Now what I'm trying to do is I will try to calculate the frequency of pair of pixel. Now listen to this. First, I'm considering vertical. Okay, vertically, this CM for the image, this matrix that I'm creating is somewhat like this. So this three actually represents the relation between zero and zero. This number actually represents the relation between zero and one. This number is actually representing the relation between two and zero, right? So on. Now, what this three is saying to me? What is the relation between zero and zero? Now you need to look vertically. You see vertically, there is one pair of 0, 0, there is another pair of 0, 0, and there is a third pair of 0, 0. So you wrote 3. For 1, there is one pair of 1, 1, There is another pair of 1 1, so you wrote 2, 2 here, right? 1 1 is here, no? 2. So basically, I have an image, but I'm not giving entire image simply to the model. I'm trying to extract that this particular image has this kind of color histogram, has this kind of GLCM matrix. So I'm giving some features, some learning, some patterns to the model to learn. If you come to the horizontal, if you look for vertical, there were three pairs, but horizontal only one and two pair are there. If you see, there is no third horizontal pair, so only two comes here. Okay, so this is another feature extraction technique. How can we extract a unique feature about that image that the model can learn? Then comes your local binary pattern. Okay, LBP. Now this is pretty interesting, very simple also. If you look, if this is the image, okay, this is the image, and this is the pixel values of the image. Our center one is the threshold, okay, because LBP local binary pattern is itself a matrix. So for every pixel in the image, you find the LBP number. How to find the LBP number? You take a pixel and take the surrounding pixels. If the surrounding value is more than the main pixel, replace it by 1, else replace it by 0. So 70 is greater than 50. I created 1. 30 is greater than 50. I wrote 0. 30 is less than 50. I wrote 0. And here 90 and 60 are greater than 50. I wrote 1. So the pattern you get here is 0, 0, 0, 1, 1, 0, 0, 1. So you lined up everything together. But I would suggest usually we take clockwise. So the pattern should be 1, 0, 0, 1, 1, 0, 0, 0. Right? And then we have the pattern here, and we understand how to create a binary number into decimal number. I hope you know that. So now we have the binary number that will get the decimal number. So what I did is I'm trying to find the local pattern. I'm looking at the what I'm looking at the local surrounding, and I'm seeing which value is greater and which value is less than. So these techniques are actually very specific and particular to that image only, right? Next is shape features. You can calculate boundary, that means perimeter. You can calculate area. You can calculate compactness, density, volume. So these are the shape features that you can calculate and give to your model. And another last technique that I use is HOG, that is histogram of oriented gradient features. Don't worry, I'll try to explain it as easy as possible. If you look here, this is an image. So this is how your image looks like. You have taken a block. This is a 2 by 2 block, right? So these are blocks. If you look at the cell, if you look at the cell, this is the intensity orientation in a cell. I'll explain you how. Basically, if I am standing at this point, I am standing at this point, in which direction the intensity is increasing? If you see from standing here, going down, because this is more intense, more darker part in the image, right? So this is basically telling you where the incentives, where the intensity is flowing in the image. We will not go behind the mathematics of this. I'm telling you these are the feature extraction techniques. So I will show you how we can code that. This is in Python. Now before showing you the code, let me tell you one thing. Python is the easiest language you will ever use. Very simple. Either you are performing deep learning, machine learning, AI. That's why I don't recommend it for data structures and competitive programming. It's better to use C++. Uh, because Python is very simple. So now if you look at the code, you will find that this is very easy. And I'll tell you why it is easy. Since the development community of Python is very huge, so a lot of people are using Python. there are a lot of ready-made code available. There are a lot of inbuilt functions. There are a lot of functions that you can directly import, which makes your life very easy. So let's go to feature extraction slide. Is this piece of code available, visible to you? Right? Is it visible? I hope so. Because it says my camera is on. Okay, so I'm hoping that my screen is visible. Now, if you look at this notebook, this is a Jupyter notebook. Okay, it is always recommended to write Python code, especially for machine learning and deep learning in Jupyter notebooks. You can use other IDEs as well. There's no compulsion, but this IDE has its certain advantages. See what I'm doing here. Very simple. I am defining I am defining a function extract color histogram. Okay, I am defining a function extract color histogram, and I'm giving argument to that function and image. You don't have to understand this code. If you are not able to understand, it's fine. It's okay. Just listen what I'm saying. I am using a CV2 library. So I imported CV2. CV2 is a Python library. And inside CV2, there is a function called as convert color. Okay. So I converted, so convert color function is used, and I'm using color BGR to HSV. Okay. So compute histogram for each HSV channel. So B is converted into H, BGR is converted into HSV channels. Okay. So if you see only two lines of code and you are able to extract the color histogram. Then GLCM metric features, right? I told you the GLCM 0 0 together, 1 1 together. So the physical orientation of pixel. So here I am using CV2.convert color. So I'm converting from BGR to gray here because I want black and white image here, right? Because you see, it helps to reduce the number of channels and reduce the number of competitions. And I'm saying distance is 1, so D is 1, angle is theta. So what is the theta that you might get in as an input, I guess, and levels symmetric. So you don't need to understand all this. Right? So in one line itself, you are able to get the GLCM matrix. Okay, and then you have extract LBP features. LBP is local binary pattern. So I'm telling you, it's very simple. Now, if I come to the output part where we extracted features, if you look at this is how your data looks. I will show you uh, ML data. So this file is of 15 GB. This single file is fixed 15 GB of data. It's a huge data. That's why it will take some time to open. So if you see here, it is 15 GB, right? And how I'm getting that? If you look at the function that I'm writing, yeah. So I'm writing a function extract features. So all the functions that I wrote above, extract color histogram, extract GLCM feature, extract LBP features, extract shape features. I am calling all that functions here. I am collecting them on the variables, and then at the end I am concatenating one after the other. Okay. So the shape is, if you look at the shape, I'm not sure if I have taken out the shape here. Okay, maybe not. I've not printed it. No problem. So I'll tell you orally. I created two features. Okay, one is with using all of these feature extraction techniques. Okay, now these all feature extraction techniques combined gives me more than 35,000 features for one image. So for one image, I'm having 35,000 columns for one row, for one image. Like this, I have 22,000 images. So you see the size of the matrix. Size of the matrix is 22,000 this side and 35,000 this side. So it's a very, very huge matrix. Okay. Is it open? No, it will take time. It's a 15 GB file, lot of data. I don't think so it will open so quickly. Okay. So I decided to create another feature set where I will only have these four. I will not have, sorry, these four. I will not have HOG features because HOG features are too much. By simply removing HOG features, I was only left with 500 features. So for one row, for one image, I had 500 columns. Okay, so that is the data I have. I can show you the smaller one. How does it looks? Let's come here. See features without HOG. If I go here, this is very huge. I might need to cancel this. Okay, maybe I can show you from the code itself. That is not an issue. Right. Okay. So let me open this. So this has like 500 columns. It's raining quite heavily outside. All right. I think it will take another 15-20 seconds. Let's see. Right. So these are the features that are generated. So this is the data you have. Now, if you look at the data, if you look at this data, this is one image. You might not able to understand this. I understand it because as humans we cannot deal with so many numbers together. But if you look where it ends, it ends at here, 543 features. And in the feature set where I had considered all the techniques, this would end at 35,000. So you can imagine how big that data is. And if you come down here, how many images you have. So this is 45,000 images, but there is a blank row. Every second row is a blank row. I would say that half of it, so 22,000 images, right? So this is the data that we get. Okay. Now we got the data, we understood how feature engineering is done. Let's move forward. So we have two data sets here. One data set is having 35,000 features with all these techniques. Feature set 2, which I just showed you, had only 500 features with all these. Okay. Next is logistic regression. Now, logistic regression is an classification algorithm. I wanted to teach you one machine learning algorithm so that you get an intuition that how do you actually learn? How does the machine learn from the data? Okay, using maths and stats. And I will leave the rest for you guys to to figure out on your own in your free time. So this is the logistic regression. If you look here, it's a classification algorithm. So what's a classification algorithm? Simple yes or no. Is this a dog? Or maybe classify this animal. So it's a dog image or a cat image. You might have that data also, where you need to classify an image as a dog or cat or maybe something else. Right? So it's a classification algorithm. Data should be linearly separable. This is a very important condition for logistic regression. What is a linearly separable data? In a classification problem, if you are able to divide the data into two sets or three sets or whatever set you want to have using a line, it's a linearly separable data. This is a non-linear problem because here the decision boundary is circle, it's not a line. And linear a logistic regression only knows how to draw a line. So data should be linearly separable for sure. So the end goal of the logistic regression algorithm is to find a set of coefficients, okay, is to find set of coefficients of a line that separates the data completely after starting with random coefficient. Now what I'm trying to say here is, let me open my one note. I'll explain it. We'll come to this later. Let's add a new page here. Now what I'm saying is, if you look, let me, okay. So if you look, this is the data that you have. Okay. So this is the cross data. Let's say this is the cross data, and this is a dot data. I need to divide this, so I create a line like this. Okay. Now this is a regression line. Okay, what it is? It is a regression line. It is not a good line. Probably an ideal line would be like this, or maybe like this. Yeah, this is the best fit line. Okay, this is the best fit line. Now, what a line is? Equation of this line would be what? Let's say ax plus by plus c is equal to 0. This is the equation of the line, right? So how do I find this line? It's a question. Let me just undo this and let me create only one line. That would be, oh, do I want to erase it here? Okay, so this is the regression line. Let's say this is the regression line. And the line is ax plus by plus c is equal to 0. Now, the question is how to find this a, b, and c such that you get a line, a regression line. This is the ultimate goal of your machine learning to learn the parameters. These are hyperparameters. Okay, these are hyperparameters. Hyperparameters are those that learn from the data. Okay. So this is a hyperparameter. How do you do that? Okay, so I hope you understand this. The end goal of logistic regression algorithm is to find a set of coefficient of a line that separates the data completely after starting with random coefficients. Now this is called as a perceptron trick. Okay, I will explain you what is a perceptron trick. How do you learn? Let's say, let's say I have a data. Let's say, let me get this as well. Yeah. Okay, this is the data, and I have this dot, this cross, this. cross and this dot. This is the data, right? Now what happens is, I'll tell you. First step is step one, start with a random line. See, randomly choose a line. Any ax plus by plus c0, random. No, don't think. Start with a random line. Okay. Randomly, I chose this line. Let's say this one. This is a line. This is my first line. Okay, ax plus by plus c is equal to 0. Now I will randomly pick, okay, this side is x. Okay, I am classifying this side as x and I am classifying this side as o. I will randomly pick one data. Let's say I will pick this data and I will see whether I will ask this data whether you are correctly classified by the line or not. So the data will say yes, I am correctly classified because this is the x side and I am also x. So do not change the line. Okay. So this particular will tell you don't change the line. Don't change the line. Why? Because it works perfectly for me. So don't change. Then randomly, let's say I pick this data and this will say no, I am classified wrong. Change the line. So this will say what? Change the line. And change the line. What change? Bring it closer to me. This is what you have to do. Now to change the line from here to here, maybe I need to draw a line like this. This side is x and this side is 0. So to jump from here to here, you need to change A, you need to change B, and you need to change C. Right? So this is how you do. So randomly choose a line. Okay. Loop for 1,000 times. This is a random number. You can loop for more time, or maybe you can loop for how many number of data you have. Select the data randomly. Ask, are you misclassified with this line? If no, do nothing. If yes, apply some linear transformation so that point is classified correctly. This is how you are going to learn. Now, uh, okay, this is important. How to label regions. If you see, if you see here, this is the line. This is the line. What is the line? 2x plus 3y plus 5 is 0. This is the line. The blue section is 2x plus 3y plus 5 greater than 0. So this, any point which would fall in this section is what? 2x plus 3y plus 5 greater than 0. And here 2x plus 3y plus 5 is less than 0. This is how you label regions. So the upper side is always positive and the lower side is negative. Okay. In this case, here the green region is negative and the blue region is positive. So in such cases where the slope is positive, the upper side is the negative one and the lower side is the positive one. Okay, I can show it to you live on Desmos itself. Let me go to it pretty quickly. I'll show you. So I'm pretty sure you would be using this tool very often. X plus y plus 5 is 0. This is a line, right? And I say x plus y plus 5 greater than 0. So that becomes blue and less than 0, right? So this is how you label a region. Okay, right. Now, now you look at this. What I am doing here is, this is the data that I have. Okay, this is dot and this is cross, this is cross, this is dot. and this is the regression line. My line says that this region is dot region and this region is cross region. So this cross comes in the dot region. So this is misclassified and this dot here is misclassified, right? So what I'm doing here is I will pick this data. Let's say the line is 2x plus 3y plus 5 is 0. Let's say the line is 2x plus 3y plus 5 is 0. Okay. And you have a point 4 comma 5 which comes under the dot region. What you do is, first of all, make that 4 comma 5 4 comma 5 comma 1. You add one number and you subtract the coefficient of the line with these coordinates. So coefficient of line is 2 3 5, right? 2 3 5, and the coordinates are 4 5 1. 4 5 1. Okay, and I will subtract it. So 2 4 will give me minus 2, 3 5 will give me minus 2, 5 minus 1 will be 4. So this is the new line. So this is how you learn from the data itself. So you are learning from the data what kind of change you want to bring. If you want, I can show this live on Desmos. This line would be somewhat here now, like this. Maybe I'll give you a quick demo here. Let us open that again. So I hope you are getting how a machine learning model is able to learn, how it is learning from the data. So the equation that we had was, where is the equation? 2x plus 3y plus 5 is 0. So let me put 2x plus 3y plus 5 equal to 0. Right? I need to print this here. Yeah, 2x plus 3y plus 5 is 0. Then I have a number. How can I add a number? Add a note expression folder image. Can I pick a number? What was the number? Number was 4 comma 5. So this is 4. Oops. Yeah, and this is 5. Let me write here only 4 comma 5. Yeah. So I've got a 4 comma 5. Now my logistic regression algorithm is saying, see this point is misclassified now. This point, this point is misclassified now. Okay. And what my regression is saying that let change the line to minus 2x minus 2y plus 4. So I'll create a new line minus 2x minus 2y plus 4 equal to 0. Now see what happened is, what this happened is the line moved towards the point. The line moved. So you would say that the point is still misclassified. I know the point is still misclassified, but at least it is better than previous one. At least the error has reduced. When I loop this through 1,000 times, I will get a good result eventually. I hope this is clear. Okay. Are you getting what I'm saying? Yes, no? I'm assuming you would be getting it. Okay. So what I did here, new coefficient, okay, new coefficient is old coefficient minus coordinates, but I multiply a small number with coordinates. That number is known as learning rate. It is usually a very small number like 0.01. So what happens is that you do not bring a drastic amount of change. Okay, you do not bring a drastic amount of change. You adjust the line slowly, because if you multiply a very small number to the coordinates would be reduced, and when you subtract very less coordinates, there wouldn't be much change. So the change is very slow. That's what we want. We don't want gradual changes very quick. No, that's not how machine learns. It learns slowly, it takes time. Now, if you look at this, here I am adding the coordinates. So I had the point 1 comma 3. I converted into 1 comma 3 comma 1, and then I took 2, 3, 5, and I added 1, 3, 1. So what you get is 3, 6, 6. So 3x plus 3y plus 6 is the new line. So this is how you keep updating your line. And this is how you are updating your A, B, and C, and your machine is learning from the data. This is what is meant to learn from the data. Okay. Now I am telling you this equation. So I gave you two equations. Let me come to my one note. I gave you two equations. One equation that I gave you. What is this? Let's keep it this way. Okay. That coefficient is equal to coefficient minus learning rate times coordinates. When we were to move to the positive side, in the misclassification of negative side, when I had to move downwards, when I have to move towards negative side, I said coefficient is equal to coefficient plus learning rate times coordinates. I can replace these two equations by simply this coefficient is equal to coefficient plus learning rate times y minus y dash times coordinates. Now, what is this y minus y dash? What is this term? Y is your actual output, and y dash is your predicted output. If you see what was happening here when you said that this is plus one. Let's say this is plus one, and let's say this is minus one. Can you do that? Let's say 0 and 1. Let's say this is 0 and this is 1. You classified it as 0, but actually as plus 1, but actually the number was 0. So your actual output is 0 and your predicted output is 1. So 0 minus 1 is minus 1. So this automatically becomes minus 1. And in this case, you said it was 0, but actually it was 1, right? So y is actual minus predictor. So actually it was 1, and you said it was 0. Then it is plus 1. So this becomes this. Okay? So this is the general equation. This is how you learn. This is how you update your coefficients of the line. I hope you get it. So this is how you learn from the data. Now I applied one, two, three, four, five, six machine learning models. Okay, I applied six machine learning models, and out of those six machine learning models, on the first feature set, which had 35,000 features, this is my result. This is the accuracy. Okay, 67%, 33%, 64.99%, 31.33%, 53.68%, and this is 47. So this is very, very poor, very bad. So machine learning is not able to perform well here. See, that's the thing. If machine learning would be able to do everything, why would we get the topic of deep learning? Why would we advance? We advance in a field of science when we see that this current existing solution is not working good. When I removed the HOG features, the second feature set, which had only 500 features, the accuracy increased to somewhat 90%. Now random forest algorithm is working well. It is able to identify 90% of the data correctly. Even decision tree has improved 72%. Logistic regression went little down. But 90% is not enough. 90% is not enough. It's not a good accuracy. I need at least 97 to 99% accuracy. Okay, that's when deep learning comes into the picture. Okay, so this was machine learning. I mean, in the limited time, whatever I could tell you. Is it clear? Before moving to deep learning, can we have a yes from anyone? Okay, are you getting things? I would assume that you might not understand all of it in the first glance, but of course, you can at least get the gist of it, the idea of technology, what is happening. Now, deep learning, okay? So we have less time left. I'll try to cover it quickly. Deep learning is a subset of ML, just that algorithms are different and they are inspired by biological brain. Now, this is an overstatement. Only somewhat a small structure of skeleton is inspired. Rest mathematics is developed from our side. So saying that deep learning is inspired from biological brain is a little bit of overstatement. I'll explain you why further. In deep learning, we build neural networks. In our body, in our biological body, we have a neural network, right? We have neurons in our brain, in our complete body, we have neurons, right? Our body is a connected network of neurons. If I have to give an instruction to my hand, my brain has to give an instruction to my hand that raise your left hand. Okay, so this is the instruction: raise your left hand. So from my brain, there would be a neuron connected to a neuron connected to a neuron connected to a neuron. So this neural network will give the instruction to lift the hand. This is how neural network works. This is how we develop deep learning algorithms. So in deep learning, we build neural networks that is a network of neurons. Okay, we call these artificial neurons as perceptron. Hence, neural networks are also known as artificial neural networks or multi-layer perceptron. Okay, so what is a perceptron? A single artificial neuron that we will develop is a perceptron, and layer of it would be a multi-layer perceptron. And the best part about deep learning is there is no feature extraction, there is no feature engineering. That is automatic. Okay, this is a perceptron. This circle. This circle is a perceptron. This is the input. So this is the input. These are the features. Okay. So I will quickly explain you what perceptron is. Here, right. So if you look here, this is a perceptron. This is a perceptron. It has two things: a summation function and an activation function. Or let me draw it like this. Okay. So this is a summation function, and this is an activation function. These are the input features. Okay, that goes inside this perceptron. Each input is provided a weight. This is input x1, this is input x2, this is input x3, this is input x4. Then We also provide a bias. This goes into summation and then we get an output y predicted. This is a perceptron. What is happening here? I'll tell you. The summation function will return you the output as x1 w1 plus x2 w2 plus x3 w3 plus x4 w4 plus 1 into b, that is bias. So these is called a bias, and these weights, and these are called as weights, weights and bias. Why are we giving weightage to every input? Because I told you there is no feature engineering here. So which feature is more important? Which feature is less important? The model will decide itself. When the model will decide itself, it will give weightage. Now these weights and bias are again hyperparameters. That means these will change with time. You don't have to worry about it. You don't have to worry about it at all. It will start with random and it will learn from the data how we did in the logistic regression algorithm. Okay. Now this summation will go to the activation function here. This will come here. If the summation is greater than 0, your y prediction would be 1. If the summation is less than 0, your y prediction would be 0. If you see logically what a perceptron is doing, a perceptron is basically a drawing a line only. Because if you see, this is an equation of a line. This is an equation of a line. Right? So basically, a perceptron draws a line. So this is your data, let's say. So it is drawing a line and it is giving output 1 or 0. So if it is above, it is greater than 0, let's say this is 1 and this is 0. So basically, perceptron draws a line. So if you look here, first you have linear combination x into weight, you input into weight, plus you add a bias. Then you give that to an activation function which will give you the output. Okay, so it's a summation function and activation function. So a perceptron is basically drawing a line. So initially we start with random weights and bias, and same perceptron trick is used to update weights and bias. Okay. What if the data is non-linear? That was the main important question because logistic regression didn't dealt with the data that is not linear. The answer is if one perceptron draws single line, add one more perceptron, add another line, and then smoothen the curve like this. You see this. See, this is the data that we have. So this is clearly a non-linear data because the decision boundary should be like this. So I created two perceptron, one here and two here, one here and one here. This perceptron, let's suppose, creates a line like this, and this perceptron creates a line like this. And my network has these two perceptrons. When I add together, I get these regions. And when I smooth it, this is my non-linear decision boundary. So perceptrons actually give you a way to classify non-linear data as well, which your logistic regression was not able to do. That's why we create a layer, a network of neurons. So this is a neural network. Okay. Now this is the input layer simply. You can't do anything about it. This is the input and this is the output. These layers are known as hidden layers. Okay. And hidden layers, each neuron is a perceptron only. So now that you understand that this is a perceptron, okay? This is a perceptron. You can use any function. We can use another function as well. These are the inputs and this is the output. When I create a neural network, let's say this is three input. Okay. In hidden layer one, I have three neurons or perceptrons. In hidden layer two, I have two perceptrons, and this is my output layer. So inside each perceptron, I have a summation function and an activation function. A summation function, activation, summation, activation. So this will come here, this will come here, and this input will come here. And I will give this is 1, this is 2, this is 3, okay, x1, x2, x3, and this is neuron 1, this is neuron 2, this is neuron 3. So this I will give weight from first input to first neuron, okay, from second input to first neuron, from third input to first neuron. Now this will go here as an input, this will go here as an input, and this will go here as an input. So this weight that you will get would be from first to second. This would be from second to second, and this would be from third to second. Now this will come here, this will come here, and this will come here. So this input is given to all the neurons. Now each neuron will give you an output. So this output will become input to this neuron, and this output will become to input to this neuron. This neuron output will become to input to this neuron, and again this neuron output will become input to this neuron, and again neuron output will become input, and you will repeat that. And then this output is becomes input to this neuron. This output becomes input to this neuron. Inside that, you have again a summation function and activation function, and you give an output. Okay? So you have that everywhere. So if you understand the basic working of one perceptron, you basically now understand the entire neural network. Now, I think so. Time is almost up. There were a few more things that I wanted to teach, but I don't think so. The time will permit us. So there is one small thing that I'd like to show you. Okay. So if you can just listen to me, I'll just open the meet. Right. Still 47 people are there. Now I wanted to show you a website. It's a very pretty interesting website. Okay. Whenever you open that website, you get image of a person. Okay. And that person does not exist. The image of the person you are seeing in your screen does not exist. It is creation of an AI model. Let me show you. Very, very interesting. Please have a look at this. Nothing technical here, just wanted to show you something. The name of the website is a person not alive, something like that. A person is not alive. AI website. A person does not exist. Sorry, a person does not exist. Does not exist. Let's say. Yeah, the person does not exist. If you look here, random face generator. Okay, you see, this is an image generated by AI. Don't you think it is very realistic? Yes or no? It's very, you look at the hairs, it's so realistic. This is generated by AI. This is not that, yeah, this is the website I was talking about. See, this person that we are seeing right now does not exist. This person does not exist. But that AI was able to create a new image. And if you see here, here they have mentioned the name of the AI model, style GAN2. So GAN basically stands for Generative Adversarial Network. So the research paper they are referring here is style GAN2. So they have created this generative model which can create this image. This person does not exist. If I refresh this, okay, let me check this. If I refresh this, now you look this person, it's very hard to believe that these images are developed by AI because you can see a problem here. This is more white than this, right? Like this suddenly became white out of nowhere, but his normal skin tone is not that white. But if you look at the hairs, everything is so like detailed, fine tuned. If you keep refreshing, this is such a clear picture. If you see, there's a small problem here, right? And you will find problems here and there. But overall, the images are too good. Right? So you can keep refreshing. This pretty much looks like AI generated. This is very realistic again, right? So what I'm trying to say is this is an incredible field of work. People are working very hard here, and very impressive. Lots of money is going in here. Lots of funding is there. Lots of research is happening. I'm very sure you use ChatGPT, right? That is an AI product, isn't it? So the startup named OpenAI is running all those things. I'll just stop sharing. Right. So I guess that's it. I wanted to cover a few more topics like convolutional neural network. We studied a simple neural network, but for plant disease detection, you need a convolutional neural network. Now, that neural network is specifically designed for image data, and the image data we had couldn't work on ANN well, but I don't think so. The time will permit us. So, if there's anything, is there anything on chat? Okay, somebody had written.
Okay, students, if you have any doubt, you can ask to sir.
Somebody wrote AI is machine mimicking human behavior and intelligence is connecting dots by which useful implementations are done. That is very close. It's a good definition, but connecting dots uh, is not the general intelligence. We are much more intelligent than that. We do more. We are emotionally attached. We remember the past. We just don't connect dots. We do connect the dots, but there is more to it. Okay. And AI is machine mimicking human behavior. Not very close. We are very far from that yet. If you have any question, if you want to say anything, you may do that. Otherwise, we may end this meet. Okay, I guess that's it.
Okay, so if no students have problem, then we can end this meeting. So thank you, sir.
Yep. Sorry, I got
So
disconnected. Yeah, sir. We
yeah,
ended
yeah.
everything. Yeah.
Yes, sir. Thank you, sir, for this wonderful session where you gave such insightful about this machine learning and deep learning and a particular case of plant disease classification. So thank you,
Right.
sir, for this session.
Thank you. Thank you, sir. I'm leaving. Okay.
So I am posting the attendance and feedback link in this meeting. So all of you fill out the form for attendance and feedback.